reaction again. Let us take the oxidation, burning of magnesium metal. Sorry, alkali metals. Now, alkali metals burn in air with the formation of the respective oxide. Say, for example, lithium. Lithium, when it burns, there is formation of a lithium monoxide. Lithium monoxide. You please wait. A correction is needed. Okay. All right. So let us continue. So alkali metals burn in air with the formation of the respective oxide. Say, for example, lithium burns in oxygen or air with the formation of a Li2O. That is lithium monoxide.
So you're not sharing
Monoxide.
the screen.
Lithium monoxide is formed. You have seen that. We take sodium. When sodium burns in air, there is formation of a sodium peroxide. Say sodium, it burns in air with the formation of a sodium peroxide. Na2O2, it is a peroxide. So sodium gives peroxide when burns in air. Now take the other metals, say potassium, rubidium, cesium, etc. They give superoxides. They give superoxides. Say, for example, potassium. Potassium plus oxygen giving potassium superoxide KO2. That is a superoxide. Similarly, rubidium and cesium, all these give superoxides. And they have the general formula MO2, MO2 superoxide. In superoxide, the metal is in the +1 oxidation state. The oxidation state of the metal, that is +1. For example, potassium, that is +1. And what about oxygen? You know, superoxide ion, O2 ion is -1. O2 ion is -1. If I ask you to make the correction.
Sir,
Yes. Yes.
sir,
Huh?
so the screen sharing is off.
Sorry. Screen sharing നടക്കുന്നു. ഞാനൊരു പ്രശ്നത്തിൽ സ്ക്രീൻ ഷെയറിംഗ് ഓഫാണ്. Now, is it all right? Okay.
Yes,
Okay.
yes,
So,
sir.
in the superoxide, the metal, potassium, rubidium, and cesium, they have +1 oxidation state. The superoxide ion, that is O2 -1 ion. I asked you to make the correction. That is in page number, do you remember? Page number 6. Page number 6, point number 18. Page number 6, Point number 18. Superoxide O2 minus 1. O2 minus 1 is a paramagnetic because of one unpaired electron in the pi star 2p molecular orbital. Now you come back to page number 4. That is point number 13. Point number 13. Page number 4. Point number 13. The superoxide O2 minus 1. O2 is minus 1 here. The superoxide ion is minus 1 here. If it is so, what will be the oxidation number of oxygen? What will be the oxidation number of oxygen in the superoxide ion? You know, superoxide ion is a O2 minus 1 ion. It is having minus 1 charge. The oxidation number of oxygen is equal to X. Let it be X. There are two oxygens, so X into 2. X into 2. That is equal to O2 minus 1. So the charge is equal to minus 1. Therefore, 2x is equal to minus 1. Therefore, x is equal to minus 1 by 2. You make that correction also. I asked you to make the correction. The metal is in the plus 1 oxidation state. Page number 4, point number 13. The superoxide, in the superoxide, oxidation number of oxygen is equal to minus half. It is a minus half. It is not minus 1. Minus 1 is for O2 ion. O2 ion, that is minus 1. O2 ion is minus 1. While superoxide ion is minus 1. While the oxidation number of oxygen is equal to minus half. So make that correction also. So the questions will be like this. Name an alkali metal which burns in air with the formation of a monoxide. Monoxide, that is lithium. Lithium. Name an alkali metal that burns in air with the formation of superoxide. The answer will be potassium, rubidium, or cesium. Potassium, rubidium, or cesium. All these can give the superoxides. We have to see one more reaction, that is its action with water. You have studied the reaction of alkali metals, the reaction of alkali metals with water. You have studied that. The reaction of alkali metals with water you have studied. You know, alkali metals are highly reactive. They are highly reactive metals. Why alkali metals are highly reactive? It's because alkali metals are large in size and they have low ionization enthalpy also. They are large in size, highly electropositive, large in size, so highly electropositive, and so they have low ionization enthalpy, so they are highly reactive. So alkali metals react with water. Say for example, you take sodium, reaction of sodium plus water. You take sodium plus water. Sodium reacts with the cold water with the formation of sodium hydroxide. That's an alkali plus hydrogen. There is formation of hydrogen. Similarly, you take potassium. Potassium reacts with cold water with the formation of potassium hydroxide KOH plus hydrogen gas. To balance the equation, you can write 2Na, 2H2O, 2NaOH. Here also 2K, 2H2O, and 2KOH. There is formation of the corresponding metal hydroxide. Sodium reacts vigorously, violently with water with the formation of hydrogen gas and sodium hydroxide. Similarly, potassium also reacts with the water vigorously. Violent reaction takes place. with the formation of potassium hydroxide and hydrogen gas. The reaction is highly exothermic. The reaction is highly exothermic, and therefore hydrogen liberated catches fire. Hydrogen liberated catches fire. It is so exothermic that hydrogen gas catches fire. Such vigorous, violent reaction takes place when alkali metal reacts with the water. You compare the reactivities of the alkali metals. Among the alkali metals, lithium is less vigorous in its action with water. Lithium is less vigorous, less vigorous with the water, less vigorous in its reaction with water. That is because, the reason is this, because, say, lithium is very small in size. It is a very small atom. It is a small in size because small in size, and there is very high hydration enthalpy and high hydration enthalpy. Hydration, hydration enthalpy. Hydration enthalpy is a very high value for lithium ion. So, lithium is found to be less vigorous in its action with water, while sodium, potassium, rubidium, cesium, etc., they react violently. They react violently with water. Regarding the reactivity, lithium is the least reactive. That is the least reactive. The low reactivity of lithium is due to the small size of the lithium atom and the high hydration enthalpy of Li plus ion, lithium ion. So that's about the reaction with the water, reaction with the water. Now let us take one more reaction of alkali metals. That is its reducing activity. You know, alkali metals, all the alkali metals are very good reducing agents. All these are very good reducing agents. All these are reducing agents. So the reducing activity, reducing, reducing action. All the alkali metals are good reducing agents. All these are reducing agents. You know what are reducing agents? Reducing agents. Say, you can explain reducing agent in terms of electronic concepts. In electronic concepts, what is a reducing agent? Reducing agent is one which can donate electron, which can lose electron. So reducing agent is, that is a electron donor. Electron donor, that is reducing agents. All these are very good reducing agents because the outermost electron can be easily removed. In alkali metals, as we know, alkali metals are the largest atoms in each period. In each period, alkali metals are the largest atoms. And so, the outermost electron, the valence electron, can be easily removed. And therefore, alkali metals act as very good reducing agents. Electron donors, they are very good electron donors. If we compare the reducing power, the reducing action, can see that lithium is the best reducing agent. Lithium is the best reducing agent. The best reducing agent. The best electron donor. The best electron donor. The best reducing agent is lithium. That is the best reducing agent. You can study that from the the electrode potential that we can study next year. Electrode potential. So for the time being, you remember that lithium is the best reducing agent, the best electron donor among all the elements, metals and non-metals, metals and non-metals. The best reducing agent is lithium. You consider the reactivity series. The reactivity series. In the reactivity series, you can see lithium is at the topmost position. In the 10th standard, you studied potassium is the most reactive element. But if we consider the electrode potentials, the reduction electrode potentials, say lithium has the largest negative electrode potential, and so it is the best reducing agent. More details we can see next year in the chapter electrochemistry. There is a chapter electrochemistry. Then the electron donating activity, electron accepting activity, that is a reducing action, and oxidizing action, all these things will be coming there. Not only that, we can explain the reducing activity as well as the oxidizing activity in terms of the electrode potential. There is a term called electrode potential that you can see next year. So among the alkali metals, not only alkali metals, among all the elements, lithium is the best reducing agent. So it is the best electron donor. It is the best electron donor. So that is all about the alkali metals. It finishes group 1 alkali metals. We forgot to discuss these points last day. So we have completed the formation of the superoxide ion, then the oxidation number of oxygen in the superoxide ion, O2 minus 1 ion, O2 minus 1 ion. What is the oxidation number of oxygen? That's equal to minus half. Then reaction with water. That also we did not discuss yesterday. Reaction with water. Alkali metals can react with water with the formation of hydrogen gas. Say lithium, sodium, potassium, all these can react with water with the formation of the metal hydroxide and hydrogen gas. Say in the case of potassium, sodium, etc., the reaction is highly exothermic, and therefore hydrogen gas liberated easily catches fire. The reaction is so vigorous, it is so violent. But in the case of lithium, that is found to be less reactive among the alkali metals. The less reactivity of lithium is due to two factors. One, lithium is the smallest atom among the alkali metals, smallest atom. So electron cannot be easily removed compared to other atoms. Okay. Then there is a high, the hydration enthalpy for Li plus ion. Li plus ion, there is a high hydration enthalpy. Due to high hydration enthalpy, the compounds of lithium are seen in the hydrated form. Hydrated form. There will be water of crystallization. We have studied the 10th standard. Say there are some compounds when they crystallize, compounds crystallize, water molecules are also carried along with the compound, the molecule, the crystal. In the crystal, there will be water molecules. So the water molecules seen in the crystals are called water of crystallization or water of hydration. Do you remember washing soda, 10th standard, washing soda, Na2CO3, 10H2, 10H2. Do you remember say CaSO4 2H2O, gypsum, CaSO4 2H2O, water of crystallization, water of hydration. Similarly, plaster of Paris, that is CaSO4 twice H2O, or CaSO4 half H2O you are studying. So then green vitriol or blue vitriol, copper sulfate, CuSO4 5H2O. So the water molecules seen in crystals along with the crystals are known as water of crystallization. Here lithium gives hydrated salts. For example, LiCl2H2O. While the others, sodium, potassium, etc., they do not give hydrated salts. Only lithium gives hydrated salts. That's because lithium has very high hydration enthalpy. Very high hydration enthalpy. So lithium gives the hydrated salts. Okay, so that's about the alkali metals. Now let us go to the next chapter. That is okay. What is the next chapter? That is alkaline earth metals. Alkaline earth metals. We are dealing with the S block elements. S block elements. You know, in the S block elements, say the last electron enters the S level. Among the S block elements, we have two groups to see. One is group 1 alkali metals, and the second is group 2 alkaline earth metals. So now let us see group 2. Group 2 elements are known as alkaline earth metals, alkaline earth metals, alkaline earth metals. All these are metals, alkaline earth metals. That is also belonging to the S block elements. Second group, alkaline earth metals. Do you remember which are the elements present in the second group? You must study at least 2-3 groups. Say group 1, alkali metals, group 2, alkaline earth metals, then group 13, aluminum group, boron, then group 14, that is a carbon family. You have to see that also this year. Then the halogens, group 17, and lastly 18th group, that is noble gas. Okay, you come to group 2 or alkaline earth metals. Which are the elements present in the group 2 alkaline earth metals? Do you remember the elements? They are beryllium, okay, come on, magnesium, calcium, strontium, barium, and radium. These are the elements present in group 2. Beryllium, magnesium, calcium, strontium, barium, and radium, the group 2 metals, alkaline earth metals. Among these, beryllium is not considered as an alkaline earth metal. That's a member of a group 2. That's right. While the others are generally known as alkaline earths. Alkaline earths, alkaline earth metals, magnesium, calcium, strontium, barium, radium. Then, among these, radium is a radioactive metal. That is a radioactive metal. Radioactivity, you know, what is radioactivity? Do you remember that? Radioactivity. Say, we have the nucleus, atomic nucleus, and we have the orbit. So this is the nucleus. From the nucleus, this is the nucleus of the atom. From the nucleus of the atom, say some kind of mysterious radiations are coming out. And that process is called radioactivity. So radioactivity is the emission of some mysterious radiations from the nucleus of the atoms, maybe natural or artificial or synthetic. Anyhow, there is emission of mysterious radiations. And the phenomenon is called radioactivity. So, radioactivity, Henry Becquerel, it was discovered by Henry Becquerel and studied in detail by Madame Curie. Madame Curie. So, radioactivity is the disintegration of the nuclei of certain atoms with the elimination of, with the emission of some mysterious radiations. The mysterious radiations are of three types. There are alpha rays, there are beta rays, and there are gamma rays. There are three types of radiations: alpha, beta, and gamma rays. Alpha, that is a nuclei of helium, beta, electrons, while gamma, simply electromagnetic radiations. Alpha, nuclei of helium atoms, beta, electrons, fast moving electrons, while gamma, that is electromagnetic radiation, simply energy radiation. Okay, there are three types. All the three types of radiations need not come out from the nucleus at the same time. Uh, from certain nuclei, alpha rays are coming out. Some others will be emitting beta rays. And during the emission of alpha and beta rays, there may be emission of gamma radiations also. So all these are produced at the same time. No, it is not like that. That depends. More details we can see when you deal with the radioactivity in modern physics. Okay. So radium is radioactive element. And the radiations coming from radium can be used in the treatment of cancer. Cancer, radiation therapy, radiation for the treatment of cancer, tumor, radiation is given. And the radiation given is one from radium. These rays are emitted. Or cobalt 60, that is a safer, the radioactive isotope, cobalt 60, that is also used. Cobalt 60, that is also a radioactive atom. And the radiation coming from cobalt 60 isotope, that is also used for the treatment of cancer, tumor, it is used. Okay, so radium is a radioactive and it is used in the treatment of a tumor, cancer, etc. Okay, here, remember, beryllium is not considered as an alkaline earth metal. Alkaline earth metal. The others are considered as the alkaline earth metals. Okay. Now let us see the electronic configuration, the general electronic configuration of all these elements. To explain the general electronic configuration, let us take the electronic configurations of some simple elements of this group. Beryllium and sodium may be taken as the examples. You consider the electronic configuration of, say, beryllium and magnesium, the first two members of the group you take. Say, for example, you take, say, beryllium is taken. Beryllium. Atomic number of beryllium, that is equal to 4. Is equal to 4. So, the electronic configuration of beryllium, there are 4 electrons. Atomic number is equal to 4. So there are 4 electrons. And the configuration will be 1s2, 2s2, 1s2, 2s2. In the outermost level, there are 2 electrons in the s level. See, the last electron enters s level. The valence shell, the last electron enters S level. You're taking one more magnesium atomic number that's equal to 12. And the configuration will be 1s2, 2s2, 2p6, then 3s2. See here also, the outermost configuration is S2, S2, 3s2, beryllium 2s2, magnesium 3s2, calcium 4s2, etc. So in general, there will be S2 configuration in the outermost level. Now you take the inner core. This is our inner core. Inner core. 1s2, 1s2. That is the configuration of a, do you remember? 1s2. That is the electronic configuration of
Helium.
helium. Yes, it is helium. Helium, inner core, helium. Then 2s2. 2s2. You come to magnesium. In magnesium, 1s2, 2s2, 2p6. Total number of electrons, 6 plus 2 plus 2, 10. 10. And atomic number 10, that is a neon. Neon. So the inner core is of a neon. Then 3s2. 3s2. So we can write the general electronic configuration as there is the inner core of the noble gas. So noble gas configuration as the inner core, and then there will be NS2. NS2. That is the configuration. Inner core is of a noble gas. And in the outermost level, NS2, where N is the outermost shell. N is the outermost shell. See, beryllium, N is equal to 2. Magnesium, N is equal to 3. Calcium, N is equal to 4, etc. So N is the number of the outermost shell or the valence shell. So the general electronic configuration will be noble gas configuration plus NS2, NS2, where N is the number of the outermost shell. Okay, so that's about the electronic configuration, general electronic configuration of alkaline earth metals. Now let us see the diagonal relationship. We have seen in the case of, alkali metals, we have seen diagonal relationship of lithium with, remember? Forgotten? Do you remember? The diagonal relationship of lithium with what? Lithium is diagonally related to, come
Magnesium.
on, magnesium. That's called a diagonal relationship. Okay. Similarly here also, the first member is beryllium. And which are the members? Say the members are beryllium, then magnesium, then yes, come on, calcium, strontium, barium, and radium. Now you come to the other group. After beryllium, atomic number 5, boron. After magnesium, atomic number 13, aluminum. See here. So now you take beryllium and aluminum. You can say that beryllium resembles aluminum. Beryllium resembles aluminum. And these two are diagonally arranged elements. And they show similarities in their properties. And that's called a diagonal relationship. So there is a diagonal relationship between beryllium and aluminum. So beryllium resembles aluminum, and the property is called diagonal relationship. They show similarities in their properties. As we have seen in the case of lithium and magnesium, when we are seeing with we are dealing with the alkali metals. Okay, diagonal relationship. Now, let us come to the atomic and the ionic radii. Let us take the atomic and ionic radii. Comparison of the atomic and ionic radii. You take. Compare the atomic size and ionic size of group 2 elements with those of the alkali metals. So atomic size, atomic size. You compare. What will be the comparison? So atomic size or atomic radius. Similarly, ionic size or ionic radius. You compare this with the alkali metals. Can see that the alkali metals, that is group 2 metals, have smaller size, atomic size, and ionic size compared to the corresponding alkali metals. Corresponding alkali metals, say lithium, then beryllium. Similarly, sodium, say magnesium. You compare this. You know, from left to right in a period. In a period from left to right. What about the atomic size? Do you remember? From left to right, atomic size decreases. Atomic size decreases from left to right. Left to right, atomic size decreases. Here, beryllium is smaller than lithium, or magnesium is smaller than sodium. So in general, we can say the atomic size and ionic size for alkali earth metals, group 2 metals, will be smaller than the corresponding alkali metals of the same period. Same period. The same period, the size will be like this. Say sodium, then after sodium, what is the next one? Lithium, sodium, potassium, and there is calcium. To compare this, say here calcium is smaller than potassium, magnesium is smaller than sodium, beryllium is smaller than lithium. Because in general, from left to right in a period, the atomic size decreases. That is because from left to right, the effective nuclear charge increases. Atomic number increases, and effective nuclear charge. Effective nuclear charge also increases. So the outermost electrons are pulled strongly towards the nucleus. So there is a contraction in size. There is a reduction in size. So from left to right, across a period, the atomic size decreases. That can be applied here also. The alkali inert metals are smaller than the corresponding alkali metals. The reason is this: in the alkali inert metals, the atomic number is more than that of the corresponding alkali metals, and there will be more effective nuclear charge in the alkali inert metals compared to the alkali metals. So, in general, the atomic size and ionic size or radii decreases from left to right. So alkali inert metals are smaller than the corresponding alkali metals. This is because from left to right, the effective nuclear charge is increased. There is no opening of new shells. New shells are not added. In a period, the electrons are added to the same outermost shell. In a period, the electrons are added into the same outermost shell. So new outermost shells are not added. along a period, across a period. Okay, but that is not the situation in a group. In a group, from top to bottom, new shells are added. Is it all right? New shells are added. And due to the addition of the new shells, the atomic size increases as atomic number increases. But here, as atomic number increases, from left to right, atomic number increases. When atomic number increases across a period, the atomic size decreases because the effective nuclear charge increases. And the attraction between the outermost electron and the nucleus increases from left to right. Okay. So here, let me stop now this time. Let us continue our discussion in the coming class. Um, say majority are not seen on the screen. What happened? Only 3, 4 are seen. Only 4 are seen. Okay, let us meet in the next class. Okay, thank you.